Okay, everybody, Dr. D here again. This is our Chapter 15 video, and the topic really is acid-base equilibria or aqueous equilibria. And this is really the topic in 16 also. It's just more advanced topic, so that's what we'll be focused on for the next two chapters. And there's some things scattered throughout the textbook and through the slides that I'm going to focus on here, and that is some things like acid-base definitions, what a polyprotic acid is, the strength of acids and bases, and these right here are equilibrium constants. Ka and Kb are equilibrium constants. They simply stand for acids and bases, so you treat them the same way. Products over reactants, that's all they are. Nothing new here, just a different subscript. And we'll talk about Ka and Kb and their importance in determining strength of acids and bases. Most of what I'll talk about in the video and also even in lecture will be focusing on acids, but you can just kind of apply it also to bases, so we don't need to talk about it twice. There'll be certain cases that I will mention bases on certain occasions. And then ultimately we'll talk about structure. So in the first part of this, I'm really going to cover a bunch of it right now. So the first thing I want to talk to you about is the Arrhenius definition of acids and bases. And with the Arrhenius definition, an acid basically produces the hydronium ions. So an acid produces what we call the hydronium ion, H3O positive, okay? And a base produces OH negative, okay? So when we look at like an acid and a base, here's an example of an acid, just generic acid, that's not a real acid. We say HA, and I'll do it in terms of HCl, since you all know HCl. We say the HCl combines with water to form H3O positive plus Cl negative. There's the generation of the H3O positive that makes this an acid. Okay? A base, if you will, would be something like sodium hydroxide. And this can just produce sodium ions plus hydroxide ions. And that would be a base. Okay? So this is the Arrhenius definition that tells us an acid is a hydronium ion donor, or producer, if you will. Producer of hydronium ions, and a base is a producer of hydroxide ions. Now, you will see notations like this. This is just a shorthand notation. Realize that we cannot have an H positive just floating around solution by itself. Why? Well, because remember, the major isotope of hydrogen is protium, which means it has one proton, 0 neutrons, and of course it has an electron, which means this right here has lost its electron. What's left is just a proton. So the other definition is kind of a proton donor, a hydrogen ion donor. That is the Bronsted-Lowry model. And you can't have protons just floating around in solution. They can be in plasmas, high energy situations, but a proton cannot be generated in solution. So the question becomes, well, where does it go? Well, it needs a place to go, and that's why water picks it up. And you might say, why? Well, why would water pick up a hydrogen ion? Well, it all comes down to stability and energy, as I tell you a lot in general chemistry. And in chemistry in general, the reason things happen is to reach a lower state of energy, to become more stable. So what that tells you is that this is just not very stable staying all together. And it's more stable with that hydrogen ion bound to water. And if you look at the Lewis structure of water, you shouldn't be super surprised with those two lone pairs of electrons that we could in fact have water pick up a hydrogen ion. Okay? So realize this is just shorthand notation. This is what actually happens in solution. Now let's take a look at the definition using the Bronsted-Lowry definition. I'll just put Bl there. The Bronsted-Lowry definition says that an acid is a hydrogen ion donor. Also, we say a proton donor, because a hydrogen ion is just a proton donor. And the base definition is the proton acceptor, or hydrogen ion acceptor. It's a little bit better definition. it just is a little bit more clear in terms of what is an acid and what is a base, because when you see something like excuse me, ammonia, based on the Arrhenius definition, you wouldn't realize that's a base. But what this can do is it can pick up that proton and form the NH4 positive polyatomic ion. Okay. Now, what it actually does in solutions is slightly different than it actually steals that from water and generates the hydroxide. But there's other species. I don't want to go into this right now. There's other species that can generate and pick up hydrogen ions without generating a hydroxide. So this is just a better definition. And there's even another definition, Lewis. And your book talks about this. I'm not going to hold you responsible for it that much. I want to expose you to it because it will something you'll come back to and see in other classes. But Lewis is the best definition because it deals with the electrons. And I always remember it as the opposite. An acid is an ion donor, therefore it's an electron acceptor. And a base is an electron donor. And that's a better definition because there are species that you won't even see this. Like something like this acts as an acid by accepting electrons from water, grabbing an OH, and generating a proton. You don't see it as a proton donor, but it's hydrolyzing water. So it's really dealing with the electrons. And there's others that behave in this way. So this definition really is the best. Okay, and this is all, what I'm writing here is all acid-base equilibria. And realize that acids and bases come together and form water. That's a neutralization reaction. So I've just written you the hydrogen ion and the hydroxide. But this is what they're doing. They can neutralize each other. Okay, so this is all acid-base equilibria that we're doing here. We're writing all this acid-base. And of course, I've left out all the AQs that should be, and the liquids here. That should all be in this as you write these. But this is all your acid-base equilibria. Now, another thing that's mentioned here is polyprotic acids. And polyprotic acids are just acids that can generate more than one hydrogen ion. So we got H2SO4. This is polyprotic, and specifically it's diprotic. This can give me the H positive plus the HSO4 minus. But that HSO4 minus can give me another H positive plus SO4 2 minus. No, the charge becomes more negative each hydrogen you lose. That's a diprotic acid. That's really all I need to say. You can have triprotic acids. Phosphoric acid is a triprotic acid. So just be aware of that. Now, I'm going to go on to this and talk about the strength of acids and bases and what Ka and Kb means. So, as I said, Ka and Kb are just equilibrium constants. Here is Ka, written, products over reactants. Once again, pure water. Concentration doesn't change. Liquid water doesn't need to be included in your equilibrium constant. Strong acids have Kas much greater than 1. Well, products over reactants, which means if you notice this, the way I've written this with arrows like this, that's what strong acids do. Completely ionize in solution. So much so that we basically say their equilibrium constants are all the same strong acids. They completely ionize and you have no of the molecular species left. Where weak acids, we're going to have a bunch of this still in solution. And by the way, HA is just a generic thing we use for acids. There's no compound HA. There is no A on the periodic table. So just a lone A, obviously. So here's strong acids. Here's nitric acid, sulfuric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, perchloric acid. These are your classic strong acids. They completely ionize. Concentration on the y-axis here, 0 of the molecular form left for strong acids. Here we go. Anytime you write acid-base equilibria, there have to be an acid and a base because the proton has to go somewhere. That hydrogen has to go somewhere. So in this case, nitric acid is the hydrogen ion donor. Water's there to accept it, so water acts as a base here. and picks up that hydrogen ion. That is the definition of one of the definitions we said of acids and bases. If you look at a weak acid, then most of it is still in the molecular form. The equilibria is still the same. We still have an acid donating a hydrogen ion and the water picking it up. But we used a double-sided arrow to show the equilibria and that the reaction is reversible, where this reaction is not really reversible because there's really none of this really left in solution. And it's so unfavorable that the reaction doesn't go in the opposite direction. Okay. So the next major topic then is structure. And when we talk about structure, there's two things to think about. One is the strength of the bond that the hydrogen has, so how easy it is to leave. If it's a weak bond, it can leave easier. If it's a strong bond, it's tougher. And also the stability of the species left behind. If the species left behind is very stable, it's easier for the hydrogen to leave. If it produces a very unstable species, well, it's not going to be very easy for the hydrogen to leave. Okay, so with these right here, I should tell you that in this case, the hydrogen is always attached to the oxygen, okay? That's not shown here. But Lewis structure, if you were to do a Lewis structure, it would look like this. Oxygen should be the central atom. That's what you learn in your Lewis structures. It has better bonding capacity. And all we're doing here is increasing the number of oxygens. And what that effectively does is it stabilizes the oxoanion that's left behind. Okay? Distributing that charge that's on the anion among all the oxygens and stabilizing it. So this becomes a strong acid, where this is actually fairly weak. I can barely read that, 10 to the minus 8. This is a strong acid. Okay? So that's all I'm going to say here in the video. We'll talk about this a little bit more in class. But as the number of oxygens increases, you stabilize the anion that's left in solution, and therefore it makes it easier for the hydrogen to leave, and you get to a certain point with 4 oxygens, you get a strong acid. All the rest are considered weak. Okay? Different degrees of weakness based on the Ka. This is the weakest. Now, if you want to compare these right here, we'll notice that in this case, the electronegativity is key, and that is chlorine is more electronegative. So the ability of the anion to accommodate that extra electron density increases as the electronegativity of the other atom increases. So the chlorine is the most electronegative. They're all weak acids, but the chlorine is the most electronegative. And therefore, the anion can accommodate that electronegativity, that electron density a little bit better. Because otherwise, oxygen's very electronegative, remember. So with a really weak electronegative element like iodine, it makes for a weaker acid because that anion's less stable, because the oxygen has to handle all that electron density, or more of the electron density. So that's the key here. So this is stronger. They're still all very weak, but I want you to realize the difference. Now the next one is where the hydrogen is bonded directly to the halogen. Over here, remember, all of these, the hydrogen's bound to the oxygen. Same here, hydrogen's bound to the oxygen. This is the same compound. We just added different halogens. Here it's bound directly to the halogen, and what we notice here is that HF is the only halogen acid that is not strong. All the others are considered strong acids. And we've got Kas there, but these Kas are very difficult to measure for strong acids. Okay? Because you kind of have to be able to measure what's left in solution. So a lot of people don't even report these. You have to have pretty advanced techniques to be able to detect these. So a lot of people just say that the Kas of strong acid are all the same. Sometimes I see HCl reported as 10 to the 9. Here it is 10 to the 7. Anyway, they're all really large, and we can treat them all the same as completely ionized. But it's the strength of the bond. And because this is bound directly to the halogen, this is really an ionic bond. Even though there's no metal here, it really is more of an ionic bond than a covalent bond. And what we have here is because fluorine is the most electronegative and hydrogen and fluorine are really small, creates a strong, strong ionic bond. Okay? With iodine being really large, that bond is weaker and you get a stronger acid. And that has to do with the electronegativity, but it's mainly because it's the exact opposite trend as this in terms of electronegativity. The higher electronegativity here is the stronger acid. That's because the hydrogen is not bound to the halogen. Okay, so as I mentioned, anytime you have an acid-base reaction, you have acid-base pairs. So we call, we have the acid, we call the base that's formed from the acid reacting the conjugate base. So here's my acid. This is the conjugate base. It's always removed one hydrogen. That's what makes it a conjugate. One hydrogen removed. This is the base, and this is its conjugate acid. They're always on opposite sides. That's pretty simple. You just got to memorize that. Okay? So the conjugate base for this is this, not this. Right? That's the conjugate base for this acid. Okay? That's all you really need to learn about conjugate acids and bases. Now, this is important, and we'll talk about this a lot in class, relative strength of acids and bases. Let's take a strong acid, HCl. Since it's strong, we know equilibrium lies very far to the right. That makes the chloride ion a very weak base, because remember, that's the conjugate base, so it is a base. But it's incredibly weak because the equilibrium lies to the right. Okay, now take something like HF. This is a weak acid, which means this is still a weak base, but relatively speaking, it's a stronger base than Cl negative. And since this equilibrium doesn't lie so far to the right, a bunch of this remains in solution, this can actually act as a base, pick up a hydrogen ion, and form HF in solution. That becomes important later when we talk about salts, in which I might add sodium fluoride to solution. What's going to happen to that fluoride ion? It's going to react with the hydrogen ions in water, which we really mean are this, hydronium ions, and form HF, and actually affect the pH of the solution as a salt, acting as a base. So take a look at this figure. It has a lot of information here. It's useful. We'll come back to this in class. The next thing is the autoionization of water. And I really wanted to talk about this earlier, but water reacts, and you can get this idea that this is always going to be present in solution when you have water, in very small amounts. And we could write an equilibrium constant, Kw now. We're just going to change the subscript. Products over reactants. This is pure water, so you don't need those in there. And you can see it's a pretty small number, 10 to the minus 14, which is telling you that water always ionizes itself. Think about it statistically. Some water molecules are going to collide, and one of them is going to steal a hydrogen ion from another in small amounts. And then that one's going to lose it. And this happens all the time because it's an equilibrium reaction. Forward and reverse rates are going to be the same, so this number doesn't change. It's an equilibrium constant. We're at equilibrium, so we have a small amount of hydrogen ions and hydroxide ions in solution at all times. So, because they have to be equal, because when one forms, the other one forms, we know that each of those are equal to 10 to the minus 7, because the product has to equal 10 to the minus 14. And this is where the pH scale comes from, because with pH, you're actually measuring the amount of this in solution. That's what the pH electrode is sensitive to, if you will. It works on basically electrochemistry. You're actually measuring current and things like that. So pH is simply the negative log of that concentration. We use negative log simply because our brains don't work very well with negative exponents. That's really what it is. It's convenience. So, we see that if we have 10 to the minus 7, the negative log of that is simply 7. So neutral water will have equal amounts of these, and the pH will be 7. Okay? And you can realize from this that your pH can certainly go beyond 0 and 14. You can get negative pHs and pHs greater than 14. They're just not very common, but depending on the concentration you put in, obviously, I can get negative numbers, and I can get numbers greater than 14. So just realize that. Okay, so because of this right here, we can just, do the math, and we can realize that the negative log of the KW gives me this. If I take the negative log of both sides, rearrange that mathematically, and what we basically get is pH and POH. POE stands for negative log. You can get a pKa. Okay, which is the negative log of the Ka. Okay, so the PA is always going to be meaning negative log. That's what it stands for, basically. So this is just a simplified form, and we'll spend time on this in class. I like to stress this in class because I think it's an important skill, and it becomes useful to you later on, pH. So this video is getting a little long. I've already talked about polyprotic acids. So the last thing then is acid-base properties of salts. And I've already touched on this a little bit. And here's the exact example I gave. Here's HF. It's a weak acid, so it does this in solution, but it doesn't do it to an appreciable extent. We still have a bunch of this left in solution. But now imagine instead of adding HF, you're adding a salt. A salt is really just a cation from a base and an anion from an acid. So you can imagine sodium hydroxide and HF combined to give you NaF and H2O. That's what the neutralization reaction would give you. If you miss sodium hydroxide in HF, you get sodium fluoride and water. So this is considered a salt. So realize now, if I put sodium fluoride in solution, because sodium hydroxide is a strong base, the sodium doesn't do anything in solution. It just stays as sodium ions. But because HF is a weak acid, the fluoride ion wants to do something in solution, right? And what it does is it reacts with water to form HF. So just think about where the equilibrium lies. For HF, the equilibrium lies far to the left. So if I add fluoride ion to solution, some HF is going to form. For sodium hydroxide, the equilibrium lies way to the right. So if I add sodium chloride to solution, nothing happens because the sodium ion doesn't want to form sodium hydroxide, and the chloride ion, because HCl is a strong acid, doesn't want to form hydrochloric acid. So sodium chloride does nothing in solution to change the pH. But this does change the pH because it is effectively generating hydroxide and therefore will raise the pH and acts like a base. And that is where I want to conclude the video, is with these salts. And with that, be sure to hit the material hard, and see you in class.